Here's another target molecule, and you may go ahead and pause the video immediately, and after you write down the structure and figure out how you would synthesize this compound. Okay, so let's talk through this. Relationship between these is an ortho relationship. Nitro group is meta director. And a carboxylic acid is a meta director as well. Okay, so you have two meta directors on there. Nitro group you add directly. Carboxylic acid, remember we make this carboxylic acid from an R group. And that R group is ortho-para director. So hopefully you figured that out. And then you could add an R group, whatever, a methyl group, and then you could convert that into a carboxylic acid. Oops, nope. Make an R group, which is your ortho-para director, and then before you convert it, direct your nitro group to both the ortho and para positions, getting two products, separate out those products, and then convert your R group to a carboxylic acid. Okay, so let's draw that out. Benzene, you're adding the methyl group, and remember you need an excess of benzene when you do this, because otherwise it's going to add a methyl and activate it more, and it'll add a second methyl and you'll have a mess. So you have added the methyl group, and then we're going to add the nitro group by using nitric acid and sulfuric acid. And you are going to get what you don't want, the para, and what you do want, the ortho. So you need to do a separation, which you're totally wasting the para, and then you will, after the separation, then you'll have just the ortho, and then you can add your permanganate to oxidize your alkyl group to carboxylic acid. Okay, so this is reasonable, except that you're throwing away a whole bunch of your product, and because you have an ortho-para director. And so there is a way to solve this problem, and that method is to block one of the positions. Remember the blocking group? You could add a sulfonic acid, and then you could get rid of it. If you can block one of those positions, then you can say you can block the para position. Then when you're adding nitric acid, if the para position is blocked, then you'll only get it adding ortho. So how can we do that? How can we just block the para position and not the not the ortho position. Let's take a look at that. So we'll start out again with our benzene, and instead of adding a methyl group, we're going to add something that is bulky. Okay, we're going to add something that will minimize the amount of para that could be. Minimize the amount of ortho that could be added. So let's add an isopropyl group here. And aluminum trichloride. So instead of having a methyl group there, we're going to have in that position an isopropyl group. And so this is bulky. So then when we go to add our nitro group, that nitro group then would not add in this ortho position, it would be adding in the para position, and we'd only get para. Then we could convert this to a carboxylic acid. But we don't want only para, we want only ortho. So what can we do to block this position here and get it to add only ortho? Well, this is bulky, and so whatever we add is going to go mainly to the para position. So if we add the sulfonic acid, that will take up the para position. Now if we add the nitro group that we wanted to add, it can't add to the para position. It's going to add slowly to the ortho positions. And let's stop and take a look at this a sec. The bulky, weak activator is going to direct to the ortho positions, and the strong deactivator, which is a meta-director, this is orthopara, this is a meta-director, is going to direct into the same positions. So we have these two groups working together to direct here or here. Doesn't matter where they add, it's the same position because it's got symmetry there. So beautiful, clean synthesis here. And we have now our sulfonic acid on here. We have our nitro group here, and we have our bulky isopropyl group, which can be removed to give the final product. And how do we get rid of that? Add H3O. I think I just misspoke. Sorry, I'm not quite there yet. We added a blocking group on here, so this group would add, the nitro would add to the ortho position. Now let's take the blocking group off by adding H3O, and we have a nitro group here, and we have our bulky isopropyl group there, so we're not quite to the final product yet. We have to add permanganate. I think I misspoke there. Nitro and carboxylic acid. More steps, certainly, than the previous method, but everything is clean, right? You get this bulky group, you get almost entirely the sulfonic acid adding to the para position, and that blocks that position. So the only place for the nitro group to add would be in the ortho position. That's being directed there by both groups, so they're working together, directing there. It's only one position, and then we can get rid of the sulfonic acid and convert our group into a carboxylic acid. And just remember that when you are doing a oxidation of an alkyl group, there has to be a hydrogen on there. So basically, this conversion of an R group to a carboxylic acid only works if the R must be either a methyl group or a primary or a secondary. If this was tertiary, it would be a T-butyl group, and that would be even more bulky, but the problem is you need to have a hydrogen there in order for this oxidation reaction to happen. Okay, so that's the use of a blocking group, and you can always keep that in the back of your mind if you want to block a particular position in getting a cleaner, higher yield synthesis.